Alright, so in this video, I'm going to try and illustrate what is meant by the magnetic flux, or in some cases, the magnetic flux density. Now, I'm not going to call it the magnetic flux density because it's a loose term. People use it interchangeably. Some people use it to mean actual magnetic flux, and some people use it to mean the strength of the magnetic field, which that can lead to some confusion. So for this video, and probably for your viewing sake going forward, think of it as just the magnetic flux. Now, to have sort of an intuition towards what the magnetic flux is, think of it like population density. And the reason why I say this is because this is where the confusion comes in, or why some people call it magnetic flux density. The population density, really and truly, is just how many people are in a given area. So for example, if the classroom 10 MECTEC has an area 10 square meters and there are 20 people standing in 10 MECTEC, you could say that the population density of MECTEC is 2 people per square meters. And how do you get that? You simply divide the number of people in the classroom by the total area of the classroom. So you have your 20 people divided by the total area, which is 10 square meters, which gives you a population density of 2 people per square meter. Now, in the case of the magnetic flux is simply saying simply saying how many magnetic fields are in an area. And here you have it here, how many magnetic fields are in this area. Now, the area can be in any shape, but generally speaking, and I believe for high school physics, it's just going to be a regular plane, a square or a rectangle, which is the length times width, or it might say like a loop, so it would be the length times width, or the area of that loop. You see me? So that is the flux, and the unit of the flux is the Weber, WB. Now, if you keep in mind, so back to the magnetic field itself now. So the magnetic flux is simply describing how many magnetic fields are in an area. So I made this model here where, if you look at it, I have some magnetic fields just a fly off in a space. You see me? It's a bunch of magnetic fields. Now, the magnetic field can have some strength. I don't know what it is, but the magnetic field has a strength and it just dip out in a space. Now, the magnetic flux aims to describe, how many magnetic fields are in a unit area. Now, this area can be any size. So I've prepared the model to show you where this red plate here, let me hide this, has an area of length by width. In this case, the actual dimensions is 100 millimeters by 100 millimeters. That's the area here. Now, this red arrow is to illustrate the normal vector of the plane. And all normal, when you say something is normal to a plane, it just simply means that it's perpendicular to it. It's at 90 degrees. So this arrow just shows the normal vector of the plane. You see me? So now you have your plane and you put it within a magnetic field. You see me? All the magnetic flux density, all the magnetic flux is asking is how many, or what's the size, or how many magnetic fields are in this area. Yeah, we'll go stick to that definition. How many magnetic fields are within this area? Now, keeping in mind that the magnetic field is a vector, like I said, it has a magnitude and a direction. When the plane is perpendicular to the magnetic field, you can think of the plane as getting the full effects of the magnetic field. Now, why that's important, and because these are vector quantities, if the angle of the plane changes, so if I rotate this plane here, I don't want to rotate. If I rotate this plane here, you can see that the amount of magnetic fields going through the plane is actually changing, or the intensity of it. And that's important. So you can intuitively see that the angle affects how much of the magnetic field, or how much of an impact it's having on the plane. And you can see that as you rotate around, when you go a complete 90 degrees, there are no magnetic fields going through the plane. Therefore, the magnetic flux, at least at this angle, is zero. Or there's no magnetic flux, at this angle. Now, why that's important is if you look at the formula for magnetic flux, phi is equal to the magnetic field strength times the area times the cosine of theta, is that since these are vector quantities and this is the expanded form of the dot product, you want to see how much of an impact, like I say, the magnetic flux is having on the plane, and the cos, at least in this situation, in this configuration, and this is just a configuration that people have agreed on, that is the case. So if you remember, or you didn't even have to remember, but if you take out your calculator and you say, what is the cos of 0 degrees? You'll find that the cos of 0 is 1. So the angle between the normal vector and the magnetic field, in this instance, they're parallel to each other, so the angle between them is 0. So you'll be getting the full magnetic flux. So this would simply become, when this is equal to, when cos 0 is equal to 1, it becomes this. However, as the angle changes, so say we go to an angle of 45 degrees, the amount that is going through, decreases. So if you say, what's cos 45, you get 0.7, and a way to think of it is that, you lose 30% of the magnetic field, or only 70% of the magnetic field is going through that plane, and that is why you multiply it by this. So like we say, all the magnetic flux is asking is how many magnetic fields are in a unit area. The B is the magnetic field strength, and that can be of any size. The area, it can be of any size, and the cos theta simply describes how much of the magnetic field is actually hitting the plane if it's at an angle. I hope that helps.